Hey, this is Mel Strong, and welcome to my lecture on humidity, part 2. If you haven't watched part 1, I suggest you go and do that first. Then this one will probably make a lot more sense. So, to recap from last time, we talked about two methods that we used to describe humidity. One was mixing ratio, and the other was dew point. Now, mixing ratio is probably the one that's the easiest to visualize, and it's describing how many grams of water vapor are in each kilogram of air. So it has units of grams per kilogram. Dew point is a little more abstract, but it describes at what temperature the air would become saturated. So if I say the dew point is 40 degrees, one of the things that tells you is that if I cool it down to 4 degrees tonight, I will get condensation or dew. So both of these are used to describe humidity, and what we're going to do is we're going to talk a little bit about how we might be able to change those two variables. So let's imagine I add water to the air somehow. So you can imagine maybe I'm boiling a pot of water and water is evaporating out of my pot going into the air. Then how is that affecting the dew point and the mixing ratio of the air? So if I can add water to the air by any means, both the mixing ratio and the dew point will increase. Now, the converse is also true. If I remove water from the air, both mixing ratio and dew point will both decrease. Now, key idea here, you cannot change one without changing the other. So think about mixing ratio. If I add water to the atmosphere, I can think of it like I'm adding grams of water to the atmosphere. Mixing ratio must go up. But if I add more water to the atmosphere, that means I don't have to cool it as much before it becomes saturated. So the dew point also goes up. So if one goes up, the other must go up. If one goes down, the other must go down. It's impossible to change dew point or mixing ratio either way, up or down, without changing the other one in the same way. So keep that in mind. Now, we also talked a little bit about how you might change dew point last time. And the same goes for mixing ratio, which is often a change in wind direction will result in a change in dew point or mixing ratio. So for New Mexico, where we live, if we get a wind coming, say, from the north or the northwest, that wind has come from somewhere cold, and cold air is always dry air. So generally that equates to low dew points, low mixing ratios. If we get wind coming from the southeast, that usually comes from a location that's pretty warm and has pretty high dew points and high mixing ratios, so those values will go up. Now, this is also true pretty much no matter where you live in the United States. If you're getting a north wind, that wind probably came from somewhere up in Canada where it was cold and dry. If you get a wind coming from the south, it probably came from somewhere more humid, and your mixing ratios and dew points will increase as a result. So what I'm going to do is show some practice problems here, and these are all problems that are kind of revolved around this concept. So we'll go through the questions and we'll go over the answers here. So here's the first one. It says the mixing ratio in this room today is 3 grams per kilogram. Okay, the temperature in here is 70 degrees Fahrenheit. So I go and I just turn up the thermostat and I warm up the room to 80. How has the mixing ratio changed? So here's the choices. Mixing ratio increased, decreased, didn't change, or not enough information to answer. Okay, so all we've done is we've warmed up the room. Okay, so when you have a question like this, you ask yourself, okay, did I add water to the air or did I subtract water from the air? Now all I've done is raise the temperature. So I did not add any water to the air. I did not subtract any water from the air. So the mixing ratio is still 3 grams per kilogram. Now, the reason I'm giving you this question is because in the past, some students get confused. Once we learned how temperature changes maximum mixing ratio, they tend to want to try to change the mixing ratio itself with temperature. So in other words, a lot of people on this question would say, oh, it's a warmer temperature, therefore the mixing ratio went up. No, not unless we added water. Okay, so in this case, the mixing ratio has not changed. Okay, let's look at another one. Pot of water boiling on the kitchen stove. The windows and doors are all closed. So our air in our house is sealed. How is the dew point inside the kitchen changing? Increasing, decreasing, not changing, not enough information to answer. Okay, so if I'm boiling water on the stove, then clearly I am adding water molecules up into the air. As the water is boiling, or assuming the pot is open, water molecules are coming out and going into the air in the kitchen. So if we're adding water to the air in the kitchen, that's going to increase dew point. So in this one, the dew point would be increasing. So another one. Tonight, dew starts to form on the grass outside. As it does so, how is the dew point changing overnight? Increasing, decreasing, doesn't change, not enough information. Okay, so if dew is forming, that means we have condensation. If we have condensation, that means that we're taking water molecules and we're bringing them down and we're putting them onto the grass, onto the ground somewhere, and that is removing water from the air. We have to remove water from the air to make dew. Okay, so if we're making dew, we're removing water from the air, and that is decreasing the dew point. Okay, so we're going to decrease the dew point as we remove water from the air to make the dew. Which of the following locations most likely has the highest annual average dew point? And so if you're unfamiliar with these places, you can kind of look at them on a map. But last time, if you remember, we looked on the internet at earth.nullschool.net, and we looked at where most of the water vapor in the world is, and it's along a band kind of near the equator. So if you live somewhere where you're surrounded by warm ocean and you have warm temperatures, you're going to have pretty high dew points. So of these choices, Miami is probably your best bet for having highest average dew point. Okay, dew point in this room was 54. Temperature is 75. I turned the thermostat up so the room warms to 80. How has the dew point changed? Okay, so once again, you ask yourself, did I add water to the air? Did I subtract water from the air? Or did I not add or subtract any water from the air? So all I did here is, so we know the dew point's 54, temperature's 75. So if I increase the temperature, have I added water to the air? No. Have I subtracted water from the air? No. Dew point, still 54. Okay, so dew point has not changed. Okay, similar to one that we seen just a minute ago. A pot of water is boiling on the kitchen stove. Windows and doors are all closed. How is the mixing ratio inside the kitchen changing? So again, if we're boiling water on the stove, that water is coming out of the pot going into the air. We're literally adding grams of water to the air. So the mixing ratio is increasing. Wind has been blowing from the west for several days. It suddenly shifts directions and starts blowing from the east. How is the dew point likely change? So we just kind of talked about this. So if it's coming from the west, it's coming from off the Pacific Ocean. The Pacific Ocean is very cold, and the dew points are usually going to be very low. Over here, coming from the east, if we trace that air back somewhere, it probably came over maybe the Atlantic or maybe the Gulf of Mexico, and the dew points were pretty high. So most likely, the dew point has increased. Okay, dew point in this room is 54. Temperature is 75. I turn the thermostat down so the room cools to 40. Does the air become saturated? In other words, another way of asking this is, do we make dew in our room? So in order to answer that, I need to know the dew point, 54, okay? Then I need to know, are we cooling it down to or below the dew point? Yes, we're cooling it down to 40. That's below 54. So we are going to make dew. We are going to saturate the air. So yes. Same question, except I added one more sentence. Does the dew point change? Okay, so to illustrate what happens here, let's consider, I got two thermometers. One measures temperature, One measures dew point, let's say. Okay, so right now the temperature is above dew point, and let's say I cool down the room. All right, or maybe this is happening outside, doesn't matter. So I cool it down 10 degrees. Temperatures drop 10 degrees, dew point has not changed. Why has dew point not changed? We haven't taken any water or added any water from the atmosphere. Cool it down further. Now it's 60. Dew point still hasn't changed. Same amount of water in the air. Now we drop it down to 50, and at 50 degrees, air is saturated. Okay, so from this point forward, we're going to start making dew. So right at 50, where the temperature equals the dew point, right? At this point right here, both of those values are the same. The air is saturated. And what we would get at this instant in time would be like microscopic dew, tiny, tiny little particles you could hardly see. But as I cool it further below 50, those little dew droplets are going to start to grow larger and larger. Now, as I start to grow dew larger and larger, I have to take water molecules out of the air and put them down onto the ground, like the grass, or if this is happening inside, it would be on the walls. So here we are at 50. I'm going to cool it further down to 40, and notice what happens. Dew point has to change with temperature. So if the temperature drops to 40, the dew point also has to drop to 40. And if I drop it further to 30, the dew point still has to follow the temperature and also go down to 30. One of the laws to keep in mind in your head, dew point can never be higher than temperature. Okay, dew point can never be higher than temperature. So here they're the same. You can have temperature higher than dew point, but you can't have dew point higher than temperature. Okay. Okay. Monsoon season in New Mexico. And we notice that over several days, the dew point is decreasing, right? So let's imagine it's in August. And we notice that the dew point has been decreasing for several days. How will this most likely affect our weather? So if dew point goes down, that means there's less water molecules in the air. If there's less water molecules in the air, you're going to have a harder time making precipitation, right? So if you want to make a cumulonimbus, a thunderstorm, you need to have water vapor available for that to happen. So when dew point goes down, the chance of precipitation goes down with it usually. So most likely we would have a lower chance of precipitation. Okay, story problem. Dew point is 52 today. Does not change for the next 24 hours. At sunrise, the temperature is 68. By noon, the temperature is 85. By 4, the temperature is 94. When do we have the highest concentration of water molecules in the air? Is it at sunrise? Is it at noon? Is it at 4? The amount of water in the air doesn't change. Not enough information to determine. So what do you think about that one? So the key to this question is in the first sentence. It says, the dew point is 52 and does not change for the next 24 hours. So the only way I can change dew point is to add water to the air or subtract water from the air. The fact that the dew point is not changing, it tells me it does not change for 24 hours. So the amount of water in the air is not going to change for 24 hours. So D, the amount of water in the air does not change. So you have to, in your mind, keep separate temperature from dew point. Temperature is going to fluctuate up and down every day. Dew point often remains constant all day long for day after day after day sometimes. So today we're introducing a third way to describe humidity, which is relative humidity. Turns out relative humidity is the most common way that humidity is described to the general public, but it's also completely misunderstood by almost everybody. We're going to talk about why it's so confusing in a minute. But you've probably heard relative humidity before. In a weather report, they might say something like, the relative humidity is 35%. Okay, so before we explain what that means, let's make a point to explain what it does not mean. It does not mean that the air is 35% water vapor. Because in the last lecture, one of the things we talked about is that water vapor ranges somewhere between 0 and almost 4% of the total gases in the atmosphere. So there's no way that it could be 35% of total gases. So it does not mean that. We can define relative humidity as this fraction, where we're looking at the current mixing ratio that's on the top divided by the maximum possible mixing ratio at the current temperature in the denominator. Now, for this class, generally speaking, you're going to be given the top. You're going to be given what the current mixing ratio is. And the bottom number, we're going to have to look up from the table that we had last time. So then we take that fraction and we multiply it by 100 to turn it into a percent. So relative humidity is given as a percent between 0 and 100%. So what does this tell you? Well, the percentage tells you how close you are to saturation. So 100% relative humidity means the air is saturated, meaning it can't hold any more water vapor. Okay? So we're going to do a sample problem, and here's an example of the type of problem that we would see. So the mixing ratio is 4 grams per kilogram. The temperature is 80 degrees Fahrenheit. What is the relative humidity? So the first thing I do is I write out the definition of relative humidity. It's the current mixing ratio divided by the maximum possible mixing ratio at the current temperature times 100. Okay, so what do we know? So the current mixing ratio is given to us. That's 4 grams per kilogram. So I can put that in on the top. Now, the maximum possible mixing ratio at the current temperature. The temperature is 80 degrees. So I've got to go back to the graph that we used last time. Here's 80 degrees. The maximum possible mixing ratio, 27.01 grams per kilogram. So I'm going to put that in. 27.01 grams per kilogram times 100. All right, so I'm going to do that calculation. 4 divided by 27.01 times 100, and I get 14.8%. Okay, so that's my relative humidity. All right, so now what I'm going to do is I'm going to change the problem by just changing one little thing, which is, let's go back to the original problem, and let's say that it's 80 degrees in the afternoon when all this happens, and then the sun goes down and becomes cooler, and it cools off overnight, and it cools down to 50 degrees. And everything else stays the same. The mixing ratio is still the same. So let's make a new calculation of relative humidity. All right, so back to this. What do we know? Well, we know that the top of the fraction is still the same. But now the bottom of the fraction has a different number because we're at the different temperature. So I go back to the table. 50 degrees, the maximum possible mixing ratio is 9.24 grams per kilogram. So I'm going to put that in. 9.24 grams per kilogram times 100. Okay, so now we will do that math. So I've got 4 divided by 9.24 times 100 is 43.3%. Okay, so here is the point, and this is a really important one. I'm going to say this more than once. The relative humidity was about 15%, and then it jumps up to 43, so it more than doubles. Right? So if I went to the average person on the street and I told them that this morning or this afternoon the relative humidity was about 15%, and then tonight it went up, it more than doubled. Most people would think that we must have more water in the air because the relative humidity went up. If the relative humidity doubled, most people would think, oh, we must have double the amount of water in the air. because that's what humidity describes. Except that's not what happened, because the mixing ratio is the same for both of these. The mixing ratio tells us how much water is in the air. There's 4 grams for every box, every 1 kilogram box of air. So the relative humidity went up not because there's more water in the air, but just because it's a colder temperature. This is why relative humidity is so confusing to people. The general public thinks that when relative humidity goes up, the air got more humid. There's more water in the air. But in fact, that's not what happened at all. The amount of water in this case stayed exactly the same. What happened was we went to a colder temperature, and the colder temperature meant we were dividing by a smaller number, which gave us a bigger answer. So what this really tells us is that initially we were pretty far from saturation, about 15%. We got closer to saturation. We're still a long ways away, but that's all this really tells us, is that the air became closer to saturation. But the amount of water in this case stayed exactly the same in both instances. And that is why relative humidity is so confusing. So with relative humidity, a lot of times we're not so much interested in the actual numbers as much as we want to know if relative humidity is going to increase, decrease, or stay the same. So if you've got one of those problems, first thing to do is write out the definition of relative humidity, which we said is the current mixing ratio divided by the maximum possible mixing ratio at the current temperature. Now these problems that we're going to see, we're trying to figure out how relative humidity is going to change. So we're going to change the temperature, we're going to change the mixing ratio. So keep in mind that even though I use the word current in here, we're projecting into the future of something that's going to happen. So it won't be current. So what you would do is, with a given problem, is write this out and think, okay, is the mixing ratio going to increase, decrease, or stay the same? And then is the maximum possible mixing ratio going to increase, decrease, or stay the same? And once you figure that out, you can figure out whether the overall answer, the relative humidity itself, is going to increase, decrease, or stay the same. But you don't actually have to do any math. You're just trying to reason out which way it's going to go. So we'll do a couple of examples here. So the mixing ratio today stays constant throughout the day. How does the relative humidity this afternoon compare to this morning? So we're going on the assumption here that this afternoon is warmer than this morning, normal day. Okay, so then we write out the definition of relative humidity and think about, okay, is the numerator going to change? Is the denominator going to change? So let's start with the top. Is the mixing ratio going to change? Here it says mixing ratio today stays constant. So the top of this fraction is going to stay constant throughout the day because we're told that. The bottom, though, maximum possible mixing ratio at the current temperature, the temperature itself is going to change. And so from the chart, we know that if we increase the temperatures throughout the day, the maximum possible mixing ratios are also going to increase. So that tells us that the bottom of this fraction is going to increase as the day gets warmer. So that means we're taking a number, even though we don't know what the number is, and we're dividing it by another number that's getting bigger. If you divide by a bigger number, you get a smaller answer. So from this, then, we can predict that the relative humidity is going to decrease as the day gets warmer. We're dividing by a bigger and bigger number as the day goes on. So we'll do another one here. You put a sealed box of air into the refrigerator. As it cools, how does the relative humidity change? So by sealed box, we can assume that there's no water that goes in or out of the box. There's some amount of water vapor in the box. We don't know how much. So we don't know the current mixing ratio. But the way the problem's set up, it's not going to change. Will the bottom of this change? Yes, we're assuming that we've got air that's probably room temperature. We're putting it in the refrigerator. It's going to start cooling. And so again, from the table, as we cool down the temperatures, we're going to have smaller and smaller maximum possible mixing ratios. So in this case, the bottom part of this fraction is becoming smaller. So now you're taking a number, you don't know the number, but whatever it is, you're dividing it by a smaller and smaller number as it gets colder and colder. So what happens to the answer? It gets bigger. If you divide by a smaller number, you get a bigger answer. So the relative humidity increases as this box gets colder. Let's do another example. So the sprinklers come on in our yard and they stay on for 30 minutes. And it says during this time the temperature outside does not change. How does the relative humidity change? So could we change the top part of this fraction? Well, if we're sending streams of water through the air in tiny droplets, there's a very good chance that a lot of that water, at least a portion of it, is going to evaporate, and we're going to add water molecules to the atmosphere. Right? That's not what a sprinkler is trying to do. A sprinkler is trying to sprinkle the grass, but it goes through the air, and you're guaranteed to have some evaporation. So if we have evaporation, we're going to increase, think of it as increasing the grams of water in the air. We're increasing the top part of this fraction. What about the bottom? Well, the bottom depends on the temperature, but the temperature says is not changing, right? So the bottom part of this fraction stays the same. So the top part gets larger, the bottom part stays the same. So overall, my answer is going to increase. So relative humidity increases as we add water to the air. Okay, here's another example. It's a little different. So on Monday, the relative humidity is 25%. On Tuesday, the relative humidity is 45%. On which day was there more water vapor in the air? Okay, so what's clear from this question is that the relative humidity increases, right? So let's think about why that might have happened. Could we increase the relative humidity by increasing the numerator of this fraction? So yes, if we increase the mixing ratio, then that would make the relative humidity go up. So that could be a possibility. But we could also make that number bigger if we're dividing by a smaller number. So if I decrease this number, and how would I decrease this number? I could decrease this number if I made it colder. So one possibility is I could have made the top number larger. Another possibility is I could make the bottom number smaller. Either way could get me from 25% to 45%. The problem is without enough information, I actually don't know which of those two things happened. Or maybe it's a little bit of both. So this is the problem with relative humidity. If I told you the dew point increases, you know the amount of water in the atmosphere had to increase. If I tell you the mixing ratio increases, you know the amount of water in the atmosphere had to increase. If I tell you the relative humidity increases, without more information, you don't know if I added more water to the air or if I just made it colder or a little bit of both. So, relative humidity is ambiguous, and a lot of times when we're dealing with relative humidity, we just don't have enough information to answer questions like this. So, a few more facts about relative humidity. A few things to keep in mind. When temperature equals dew point, your air is saturated, and your relative humidity is 100%. Okay, so remember that one. Inside a cloud, relative humidity, always 100%, or fog. Fog is a cloud on the ground. You can't have relative humidity over 100%, okay, at least not in this class. So if you're doing the math and you come up with a number over 100, you did something wrong, all right? The relative humidity usually cycles over 24 hours, whereas dew point and mixing ratio usually do not. Okay, so let me explain that one a little bit more. So if we measure temperature every hour throughout a 24-hour cycle, day after day after day, we would notice that the temperatures cycle, right? It gets warms up during the day. The hottest time is usually late afternoon. Then it cools down, and then the coldest time in the 24-hour period is usually right before the sun rises, and then the cycle continues again, right? We have this kind of what we call sine wave curve of temperature. Well, what we said now several times is that relative humidity depends on the temperature. That's on the bottom of that fraction that we keep talking about. So what that means is where the temperature is the warmest, we would expect the relative humidity to be the lowest. And where the temperature is the lowest, we would expect relative humidity to be the highest. So this is the kind of graph that you expect to see with relative humidity. In a normal 24-hour day, the dew point and the mixing ratio don't change very much. In fact, usually, especially here in New Mexico, day after day after day, you typically have a pretty constant dew point, usually, okay? But the relative humidity is always in a 24-hour cycle because the temperature is in a 24-hour cycle. So we typically see the lowest relative humidities the hottest part of the day, then they rise at night, so we see the highest relative humidities at night, and then the cycle repeats again. So again, I keep repeating myself here, but it's really important to emphasize a lot of people are super confused about relative humidity. If they have a little weather station, they look at it, and it's night, and they see the relative humidity go up. They think, oh, the air is more humid. There's more water in the air. But no, that's not what's happening. The only thing that's happening is the temperature has decreased in the nighttime, which makes the relative humidity increase. So with all this confusion then, good question would be, why in the world are we using relative humidity at all? In fact, when I started this, I said that we use relative humidity more than the other two variables. So one of the reasons is that it's related to human comfort or discomfort. So you've probably experienced these at some point. If you have a hot day with high relative humidity, you feel miserable. And we'll talk more about this in the next lecture, but a lot of it has to do with the evaporation or the lack thereof of your sweat. In fact, there is something called the heat index, sometimes referred to as a misery index. And on the y-axis here, we have relative humidity. So there's 0% to 100%. This is the temperature from 70 to 110. And these boxes are what it feels like to you. That's the heat index. So you'll notice that, for example, if you have low relative humidity, it actually will feel cooler than it really is, right? So if it's 100 degrees outside, but the relative humidity is 0%, then it feels like it's about 91, okay? So that's nice. But, of course, what's not nice is when you get to high relative humidities, right? So if you have a 100-degree day and 80% relative humidity, you end up with a heat index of 157, meaning it feels like it's 157 outside. So in New Mexico, we don't really talk about this too much. We don't have much of a heat index here because our relative humidities are usually kind of, especially in the summer, they're kind of in this range up in here. So we really don't have to worry about this too much. If you live in the southeast, for example, they deal with this a lot. Now, what we do get in New Mexico a lot is the second one here, hot day and low relative humidity. That produces desiccation, meaning that your skin dries out, right? So you know when we have these days, especially in New Mexico, they occur usually in June is the time where we have the hottest temperatures and the lowest relative humidity, and your lips are dry, and your skin is dry, and you're itchy, all that stuff, right? So that's because of low relative humidity. And then it also affects the way you feel cold temperatures as well. So when it's cold and the relative humidity is high, it does feel colder to you. Another reason that we use relative humidity is for fire danger. So when you have low relative humidity, that means it's much easier to start a fire, and then once the fire starts, it's much easier for that fire to keep burning. And then finally, it's related to evaporation rate, and we're going to talk about this in the next lecture. But when you have low relative humidity, you have very rapid evaporation. So let's go back. This is a question that they had at the beginning of this lecture. Temperature in this classroom is 75. The dew point is 54. I change the thermostat and the temperature rises to 85 degrees. As the room warms up, what happens? Dew point increases, dew point decreases, dew point doesn't change, not enough information. Well, in this case, if I just increase the temperature, I'm not increasing the amount of water in the air. I'm not decreasing the amount of water in the air. Dew point does not change. Okay, so this is what we were saying in the beginning of this lecture, that when we increase temperature and we decrease temperature, if we're not adding or subtracting water, dew points and mixing ratios don't change. But if I take this exact same problem and I just change one thing, instead of dew points, if I change it to relative humidity, now, as I warm the room up, the bottom of the fraction of relative humidity changes, right? So this is a typical problem that you might face. So as I warm the room up, I'm dividing by a number that's getting bigger, so my overall answer is getting smaller. So in this case, the relative humidity decreases. So this is what you got to keep track of. You got to keep track of dew point, mixing ratio, and relative humidity. If you add water to the air, what do each of those do? If you subtract water from the air, what do each of those do? If you increase the temperature, what do each of those do? When you lower the temperature, what do each of those do? Okay? So again, if you're one of my students on Learn, the next quiz or question is all about this. All right. Thanks for listening.